for low friction, corrosion free, fully sealed and potted with potting compound to make it completely waterproof. This is a wireless wind transmitter. The cups are 3 identical 3D printed pieces for easy storage and shipping, and the ability to replace them if they were to break or something. So this is a wireless wind instrument that I'm working on. It's using a protocol called ESP Now. Here you can see it's wirelessly connected to the Pilot. So these are some wireless wind instruments that I'm working on. It actually supports data from all kinds of sensors, not just wind sensors, with the daylight visible display. This is the current prototype board. It can take a isolated NEMA input as well. It's got an ESP32 showing the Pilot information, and if you go to pilotmfd.local in a browser, you can see the wind sensors. It supports, you could have multiple wind sensors on different sides of the boat, and it will use the upwind one. You can set it to use signal K, you can set it to use NEMA. Here we can see the data that it's actually receiving, but it can receive all types of sensors. GPS, water speed, all of that's supported. And then there's all these different display pages, and you just kind of enable the ones that you want to use. It can even display AIS ships and targets on a 5-inch, on this 5-inch screen. So this is an MPPT solar charge controller, but it can also do wind or water turbines. It can buck and boost the voltage, and since for turbines the power is relayed the flow speed cubed, it actually needs to correctly load the turbine so that the foils don't stall, and so it needs to essentially make sure that the current goes up by a factor of 4 for the speed doubling, and so the voltage input might double, and then the current input would quadruple, and then the power output would be 8 times as much. So here's a turbine generator. It's made from a drone motor that's rewound and put in a sealed box, and it outputs 3-phase. And then I've got a 3-phase rectifier here. This one just uses diodes, but I've actually built this one here, and this is a synchronous 3-phase rectifier. So it avoids diode drop, and then these are different types of turbines. And then this is what I tow behind the boat, and it's full of threaded rods, so it's heavy and it helps it to sink, but it's a torpedo shape. And then it spins the rope. The rope attaches to the generator here. And unfortunately, this setup only makes like between 1 and 2 amps at 12 volts. But part of the problem is that these 3D printed turbines have a lot of friction. They need to be smoother, and you know, I'm still trying to optimize it. So this is in contrast to solar, where essentially you want to keep a pretty constant voltage input and maybe slightly vary that to try to get the most amount of power output. With turbines, the speed is constantly changing with a gust of wind, and so the same algorithm doesn't really work for peak power tracking. Here it's got a bunch of voltage references that it can, so that it can automatically calibrate offset and scale factor for the analog to digital converter. And yeah, I mean, overall it's pretty simple. It does synchronous rectification. This design uses a special chip for discontinuous mode. And then I've got an SD card so that it can also do data logging. But it also can communicate over Bluetooth or wirelessly. This is another development. It's just an AIS monitor using a Raspberry Pi Pico and a Daisy AIS radio receiver. It's got its own onboard battery, so it can run for 8 hours. There's a speaker, so it can sound AIS alarms. So, and it's all got isolated filtered power supply. So, hopefully, if you have like some kind of transient voltage on your main power system, it will never damage this. And even if power goes out, you'll still be getting alarms from ships. It plugs into its own GPS, and then over Wi-Fi, if you want, it could connect to like other devices to plot the ships or to send both AIS and GPS data. It can also function as an anchor alarm, a standalone anchor alarm, and it can also monitor like an AIS transmitter to make sure that you're actually transmitting your position. So the motivation for making this is essentially that even if all the power fails or your main AIS receiver breaks or your antenna or anything, this is just a redundant system with its own speaker, its own battery, its own alarm that will detect ships, determine if you're on a collision course. It does all the closest point of approach calculations. It's all configurable with a web interface. And it's running MicroPython on a Raspberry Pi Pico with web browsers and web sockets and all that kind of crap. Then in a web browser, you can set some parameters for the network and alarms, and then it plots the ships. I mean, you could also connect it to something like OpenCPN to plot the ships, but the main purpose of this is just have a backup standalone alarm system to avoid collisions, really. Let me know what you think in the comments about this. I designed it in theory to fit inside this enclosure, but it's not quite right with this initial prototype because it doesn't quite fit on the corner here. I can probably clip it and make it work. So basically the motivation for this is I was sailing down the East Coast a few months ago, and I had already gone more than 200 miles that day, and it was cold and I was tired, and I got in my sleeping bag just to warm up and kind of dozed a little bit, and my boat started rocking a particular way, and I knew it was a ship's wake, so I jumped up to try to do something, and right as I was climbing out, I crashed into the side of the ship, and I tore my shoulder, and I've since healed, but it took me a long time to really recover from that, and it damaged my boat pretty bad, and it took me about a week to fix my boat. I'm lucky it didn't like lose the mast or hull the boat or anything, because I was way offshore. And it's a shame too. I mean, technically, you know, I was under sail, and when you're way out in the middle of the ocean like that, I was more than 12 miles from land, and it was like deep, like 300 feet of water everywhere. You know, correct me if I'm wrong, but collision regulations, the ship I'm the stand-on vessel. Of course, I'm not supposed to crash into a ship or anything like that, but you know, according to collision regulations, I shouldn't have to. I'm going to briefly show some of the hardware that I've been making. This is a Tiny Pilot computer. So this is the board inside the Tiny Pilot, and it's just got a radio receivers, infrared receiver, light sensor to automatically turn on and off the backlight. It's got reverse polarity. It's got over current detection, and it's got a voltage sensor so that if the USB voltage ever got too high, it will not get to the Raspberry. And it's got the inertial sensors. There's also a buzzer so that it can beep, and an EEPROM so that it can kind of automatically detect the hardware. But that's basically all there. So it's got USB-C power. It's got USB data, like for GPSs or wind instruments input. This wire is the remote control antenna, and this goes to the motor controller. Alternately, you know, I've got the Autopilot HAT, which just fits on a Raspberry Pi, and this has the same functionality, but it's not contained in its own enclosure. And but it also has a galvanically isolated NEMA port, and it can support 2 motor controllers, that way you can use an alternate UART and not take up the primary UART. This is a generic 433 megahertz remote control. They're really low cost, but they work pretty well. It's not entirely waterproof, but if you're careful with it, it works pretty well on the boat. These have random codes, so each one has to be programmed for each function with Autopilot in the web interface. So I've got 3 different versions of the control panel. This first one here has a menu button, so it's actually designed to be used with the screen. And then that way the auto actually toggles, so that's why you need to be able to see the screen, and mode toggles through the different modes. If I press the menu button, it goes into the menu, and you can go into all the different settings. For example, seeing the power consumption and things like that. I can go to wind mode, and I could enable or disengage the pilot. These other control panels, you don't need to be looking at the screen to use them, because no matter what it's in, standby will always go to standby. C will always go into compass. One of the advantages of these custom control panels compared to like the generic remote is they send alternating codes, so that if you press a button really fast, it will know exactly how many times it was pressed, and also it will sends a stop code, so it has really good timing when you press and release for manual mode. And then also the other thing about it is that it if you press a button really fast, it queues it up and makes sure that all the messages get sent. And then like finally on all of these, if you press the +1 +10 at the same time, or -1 -10 at the same time, it tacks in that direction. And you can also program all of these to take double presses. Like for example, GPS and wind press at the same time goes into true wind mode. So I've actually reverse engineered a really simple RF transmitter, and that's what's on these. That's what's actually integrated into these boards. And there's a trace antenna here for 433 megahertz built into the circuit board. This is an isolated USB to NEMA converter. You can plug this into like, you know, like a radio like this that has GPS or AIS or a depth sounder or any kind of NEMA, standard NEMA data can be converted with this, and it's galvanically isolated. So this is the regular motor controller. It's got optically isolated data input. It's just a standard H bridge, and it can power the motor in forward and reverse. It does pulse width modulation, so it can do variable speeds, and you can wire in the rudder feedback or other things like a temperature sensor. But generally, this can handle up to 7 amps continuous without heating up by more than 20 Celsius. It is a trade-off. You know, if it had a heat sink, maybe it could handle a little bit more power. Fans are kind of unreliable, especially on a boat, so that's not really a good option. But if it had a heat sink, it would be more difficult to assemble, and then it would essentially just it's difficult in the low quantities. So I've made several hundred of these, and they've been really successful. I haven't had too many complaints. You know, a few people have wired them to really high voltages and popped the TVS diode on it, but generally they work pretty well. I've got one here that I've had rigged in my boat for a few years, and no problems with it. So the regular controller, it can handle windshield wiper motors. It can handle like typical like linear actuators. This is actually kind of a small one. So like for example, it's perfectly adequate to power something like this that only draws a few amps while it's moving. This is similar. These are really nice. They use ball recirculating ball screws, so they're really high efficiency, but they're kind of hard to get. This one, I really like it because it's got a 150 millimeter per second speed, so it can move my rudder all the way over in 2 seconds. Let's see. If you see in manual control, you know, this is a lot faster than most. So I got this actuator off AliExpress, and as you can see, it's not really marine grade. That's my biggest issue with it, is it rusts a bit, but otherwise I've been using this. I sailed all the way to Newfoundland and back with it, and it works really well, except the end stop switches burned out, so I opened it up and I rewired it to bypass those. But otherwise, it's got a higher speed of travel. I mean, if you look at the speed that it moves, that's a lot better than most of these other actuators. Like this one right here, it has a ball screw. These are really nice. They have a lot of force, and they're really efficient, but they're also, you know, unless you can get it secondhand. I got this in a what do you call that? Like a consignment shop. You know, I tend to prefer this one just because the speed that it moves, and the cost is a lot less too. And they make all different sizes and different speeds and forces and different powers. And so what I do here is I just hose clamp on a bit of plastic that I have holes drilled into, and then that snaps onto the tiller pilot pin, which is mounted right under the tiller here. And then there's this piece. So basically it snaps on like this, and you can see that it only takes about 2 seconds to move the rudder plus and minus 30, which really makes a big difference in when you're surfing on waves and getting thrown around. Now a lot of boats have larger requirements, so I go ahead and I have designed a more powerful motor controller. It's got some switching regulators. It's a little bit more efficient. This one has double MOSFETs for each channel, so it can handle twice as much power. But it's physically larger, and it makes use of the PCB sort of as a heat sink. That's why there's these big copper areas. It also can handle 24 volts, and it's also got a clutch output. Okay, so this one can actually handle smaller hydraulic pumps, but for even larger, I've got here, there's 4 MOSFETs in parallel, and it's an even larger version. And this one can do 30 amp continuous and also 24 volts. And it's just an even larger version. This enclosure, you know, these enclosures, they're not waterproof. It's meant to be mounted in the boat in a dry area, but they allow ventilation through, but keep splashes off and dust out. So I've also 3D printed these rudder feedback. I use either ASA or polycarbonate so they can be outside, and this one's fully waterproof. So basically it's just a 3D printed enclosure, but there's a Delrin bushing in here, so it's got a pretty smooth fit with pretty good tolerance. And then there's a diametrically magnetized magnet on this shaft here that it sits just above this potted encapsulated angular Hall sensor, and then that outputs a reading that goes back into the motor controller. And then you can optionally set this up to prevent the motor from stalling, but the motor controllers do measure the current through the motor, so if that goes above the setting, it will also detect stalling. So I'm working on a much more comprehensive video detailing Pilot, installing it, using it, everything. So yeah, that was just like a really quick rundown of some of the stuff that I'm working on and what I'm building. You can see also here the wind sensors that are potted. It's got an ESP32, and then it's just got a voltage converter so that it can be powered from 5 to 40 volts. That way you could wire it on like an anchor light or something and set it up so that at 5 volts it powers the wind sensor, but not the light, but at 12 volts it would power the light as well.